The reason we are so excited about the normal distribution and the reason we care so much about it in this class is not that it's one of the most common probability distributions that you'll ever see anywhere, although it is. The reason we care about it so much is because of sampling. So to think about sampling, let me give you just a quick introduction to standardized normal random variables, which we talked about a little bit earlier. But let me see if I can also bring that into the discussion as to the motivation for this choice in the first place. If you take a random variable x, which has a normal distribution and a mean of 10, standard deviation of 3, for instance, just any such case, and you subtract 3, subtract 10, that is, subtract the mean, and divide by the standard deviation 3, you still have a normal distribution. That is, the shape of this bell curve can get shifted around when you subtract 10 or add a value to it. In this case, subtracting 10 shifts it over. And then dividing by 3 will kind of squish it in such a way that the actual formula stays the same. And that bell shapedness is not distorted by shifting, subtracting or adding a value, or rescaling, dividing by a value. Moreover, in this case, if you subtract the mean and divide by the standard deviation, we get this special normal that has an average of 0. And that should make sense, right? If the average of x is 10, then what's the average of x minus 10? 0. And even x minus 10, 0 divided by 3 is still giving you an average of 0. But what's more interesting is that the standard deviation is now 1. And so I can take any normal random variable x that has any mean and standard deviation and transform it or standardize it into this shape. And a lot of times we'll call this z as a special case, signifying that it's not just any old normal random variable, it's a special one. So, keeping that in mind, let me show you what particular random variables we're going to be dealing with. Let's say we have a population. It could be a population of tourists in Waikiki or Phuket. It could be a population of MBA students in the world or in Bangkok. It could be a population of customers at the Ala Moana Shopping Center or Mabung Krong. All of these, or just on my website, right? So all of these entities in my population, let's just for sake of an example say these are all visitors to my website. I want to know whether they spend a lot of time on the website or whether they just kind of quickly go there and then go somewhere else. But I don't know how long they tend to spend, but I know that there's an average, which we can call mu for the mean. I also know that there's a standard deviation. They're not all the same. Some people come and go and they're way below average, and some people will linger on the website for days and days and days. So they'll be way above average. The population that we're considering is varied. That is, they're not all the same. There's some variability or standard deviation measuring how they tend to differ on average from that average. Now let's say that this population is large and measuring it directly is challenging. You can't go to all the tourists in Phuket or Waikiki and have them fill out a survey about how long they're staying, how much money do they earn, how many times will they get Thai massage while they're in town, or in Waikiki, how much pineapple will they eat while they're visiting. There's a question I'd like to know, but I can't possibly find everyone in the population to learn the answer to that question. So what I'm going to do is take a sample. And if I take my sample in a reasonable way, so that everyone in the population is equally likely to be included in that sample, if the sample then is more or less what we call representative of the population, then I can measure the sample mean, which we call x bar, and that's just the mean of my sample, the average time spent on the website of all the people that I'm testing, the small little group, rather than the whole population. I can also take S, which is the sample standard deviation, and I might also measure N, which is the sample size. And if I do this well, in the sense that everyone in the population is equally likely to be included in my sample over here, then I can say the following facts about the sample. X bar is a really good estimate of mu. On average, it's dead on, it's correct. It's not perfect. I might have bad luck. I might have accidentally sampled people who stay on my website for a really long time. I just might have been unfortunate. I happen to have sampled a bunch of tourists who happen to spend a lot of money or a lot of time in Waikiki. It's possible that my X bar is not equal to mu. In fact, it's likely. But I can tell you how close it tends to be to the true mean. The sample mean, the sample standard deviation is a good estimator of the actual standard deviation. And so using these two estimators for these two parameters that I don't know, I can make a lot of sensible guesses about how the whole population behaves based on these two things, based on the estimates of those values. And that sort of makes a lot of sense, I hope. But I want to talk about how to be a little more precise. So, what I can say for certainty is that the sample mean is a random variable. Right, it's a random variable. It might take on a number of different values. It could be really high, it could be really low, it could be dead on, exactly correct to the mean. But I can be much more specific. X bar is, in fact, a normal random variable. So, on average, the mean of X bar is equal to the true mean. On average, X bar is correct in that sense. But, so now I know it's bell-shaped, and that the center of that distribution is the correct mean of the population that I'm trying to